Okay, so this is some extra stuff that goes with your green sheet of notes. Okay, we already looked at the null hypothesis last week. We just went over that. There's no difference between them. And we looked at the alternative hypothesis, which we could do in several different ways, depending on what we are stating with it. Okay? These types of hypotheses are called directional or one-tailed. These are the kind that I want you to make, where you predict my experimental conditions are going to have greater results on the mass of the plants, the height of the plants, the whatever your experiment is. Okay? This one here, it's going to be different, but I don't know how. That is called a two-tailed hypothesis. It's the one I call wishy-washy, and we can tell you to take a stand and pick a side. Okay? You know, to me, that's like, okay, well, who do you think's going to win the game? Well, the two-tailed test is like saying, well, one team will win. I don't think it's going to be a tie. You know, I mean, come on, pick a side. All right. We want to make these statistics. We want to make these predictions because we want to test it with statistics. And we are going to look at a curve, a distribution. We looked at the distributions when we did our frequency diagrams, our frequency distributions, and our stem and leaf plots. Okay? With a one-tailed test, we're looking at just one end of this. With a two-tailed test, we could have it going higher or lower. So we're looking at both of them. We are going to be doing t-tests, chi-squared, and most likely linear regression, and possibly some groups will go into an ANOVA. Now, you don't know what those mean right now. I understand. Don't worry about it. But they're just different ways for us to test statistically whether your results are enough different that you can say it's because of your experiment. So, you need to define an alpha level. This is your level of significance. It's essentially it's really the error you're willing to accept. So if we use an alpha level of 0.05, that means we're saying 5 out of 100 is due to random chance, and that's okay. That is the typical one we use. for the types of experiments that we use. Any sort of medical testing, like to test a new medication, would use an alpha level of 0.001, which would be 1 out of how many? 1,000. Okay? Much more stringent conditions because of what they're testing. Now, if you look on this page with the chart, okay, that is your sampling distribution for the t-test. Do you see how across the top you have alpha levels, and you have the option of picking the one tail or the two tail. Do you see how the columns are for the one tail and the two tail? Look at those values across the top. What can you tell me for every column about the two tail alpha level versus the one tail? It's double because it gets both ends of the distribution, whereas the one-tailed only gets the one tail, the one end of it. Okay? And you see down the side, what do you have down the side? Degrees of freedom. Okay? Degrees of freedom is the number of samples that can vary. So it is always your sample size minus 1, because the last one is now locked into position because it's the only one left. Okay? Now, if you have two lists, like an experiment and a control, and there are 10 in each of those, okay? Your degrees of freedom would be 9 for your experimental group and 9 for your control group. So what are your overall degrees of freedom for this experiment? 18. Okay? So, still looking at this list, this chart, we now have, because I made it up, 18 degrees of freedom. And let's go with our typical alpha level of 0.05 for a one-tail test. What this table gives you is what is called a critical table value. So for a 0.05 one-tail and 18 degrees of freedom, what is your critical table value? We have a suggestion of 1.734. Do you concur? Okay. So you find your alpha level of 0.05 for your one-tailed test, and then read down until you get to 18 degrees of freedom. So what are you going to do with this? You are going to compare your critical table value with a calculated test statistic. So when I teach you how to actually do them on the calculator, you will calculate your own test statistic. The first practice set in here doesn't have you calculating anything. We're going to save that for next week. But what you want to do is you want to look at how does your calculated value compare with the critical table value. Okay? So, if your test value is less than your critical table value, you fail to reject your null hypothesis. If your test value is greater than your critical table value, you reject your null hypothesis. If you reject your null hypothesis, that means you support your alternative hypothesis. If you fail to reject your null hypothesis, you do not support your alternative hypothesis. And that is the whole point of doing your statistical test, is to see, does my data actually support my hypothesis, my alternative hypothesis, my research hypothesis. Notice statistics uses this kind of funny language of fail to reject the null hypothesis. Seems logical to say we accept our alternative hypothesis, but that is not the language of statistics. Okay? Now, read this, because I just sort of highlighted and summarized some things. So make sure you read this. What I want you to do, either by using some time in here today or Wednesday, or doing it for homework, practice set 2 is due next Monday. So next Monday is March 4th. Okay? And you see practice set 2? Wow, I'm having trouble writing, but put your answers on notebook paper. There is absolutely no possible conceivable room on this. Okay? If you do not put it on notebook paper, I will give you a 0 and will not accept it. Okay? Again, I'm going to allow 1 paper per